This video is actually a section of a course in my channel. The course name is C Programming for Beginners. The content of this video includes the lessons of that section. Let me read the lessons to you. First is one-dimensional arrays, declaration, initialization, and accessing elements. Second is one-dimensional arrays, example, storing a list of scores. Third is strings in C as character arrays ending with the null character. Fourth is strings, declaration and basic string functions, introduction to string.h. Fifth is two-dimensional arrays, introduction the concept of matrices. Sixth is exercises. This lesson does not include the answers. Okay, let's get started. First, introduction. Why arrays? So far, when we wanted to store multiple related pieces of data like 5 student scores, we had to create separate variables, integer score 1, integer score 2, integer. This quickly becomes unmanageable for many items. Imagine needing to store 100 scores. This is where arrays come in. An array is a collection of elements of the same data type, stored in contiguous memory locations. Think of it like a list or a row of identical boxes. Second, declaration of one-dimensional arrays. Declaring a one-dimensional array tells the compiler data underscore type, what kind of data the array will hold, e.g., integer, float, char. All elements must be of this type. Array underscore name, the name you choose for your array. Size, the number of elements the array can hold. This size must be a positive integer constant. Example, integer scores 5. This declares an array named scores that can hold 5 integer values. Important note, in C, array elements are stored in memory next to each other. This is a fundamental concept. Third, initialization of one-dimensional arrays. There are several ways to initialize an array. A during declaration with values. Integer myNumbers 3 equals 10, 20, 30. This creates an array myNumbers of size 3 and assigns 10 to the first element, 20 to the second, and 30 to the third. Implicit sizing, integer myNumbers equals 10, 20, 30, 40. If you omit the size, the compiler automatically calculates it based on the number of initializers provided. Here, myNumbers will have a size of 4. Partial initialization. Int myNumbers 5 equals 10, 20. If you provide fewer initializers than the size, the remaining elements are automatically initialized to 0 for numeric types or null characters for character types. So, myNumbers would be 10, 20, 0, 0, 0. B after declaration, assigning values to individual elements. You can assign values to elements individually using their index. 4. Accessing elements in one-dimensional arrays, indexing. To access an element in an array, you use its index or subscript. This is the position of the element within the array. Crucial point. C uses zero-based indexing. This means the first element is at index 0. The second element is at index 1, and so on. For an array of size n, the last element is at index n-1. Example, for integer scores 5, scores 0 refers to the first score. Scores 1 refers to the second score. Scores 4 refers to the fifth and last score. To assign a value, scores 2 equals 85. To read a value, printf the third score is %d, scores 2. Fifth, example code, declaration, initialization, accessing. Sixth, conclusion and next steps. Arrays are fundamental. They allow us to manage collections of data efficiently. Remember, They store multiple values of the same type. They use zero-based indexing to access elements. The size must be a constant during declaration. In our next lesson, for point 02, one-dimensional arrays, example, storing a list of scores. First, introduction, the need for loops. In the last lesson, we learned that arrays let us store many values under one name. But imagine having 20 or 50 scores. Manually accessing each element like scores sub 0, scores sub 1, up to scores sub 49, is inefficient and tedious. This is where the true power of arrays is unlocked, by combining them with loops, specifically the for loop. Since array indices are just numbers, 0, 1, 2, etc., we can use a loop counter I to access every element sequentially. Second, the problem: storing and displaying 5 scores. We need to perform 3 main tasks on our array of scores. Input: read 5 scores from the user and store them in the array. Processing: calculate the total sum of the scores. Output: print all the scores and the final average. Third, code implementation, inputting scores. The loop condition I is less than 5 must be suitable for the array size. We declare an array of size 5 and a variable for the loop counter and sum. Key concept: notice how scores sub I allows the loop to sequentially target scores sub 0, then scores sub 1, and so on until the condition I is less than 5 is false. Fourth, code implementation, processing, and output. Now we'll calculate the sum and the average. Since we are dealing with integers for the sum, we should use a float for the average to ensure accuracy. Fifth, full code summary and execution walkthrough. The combination of arrays and loops makes this task simple and scalable. If we needed 50 scores, we would only change the array declaration, scores sub 50, and the loop condition I is less than 50. This is the power of using the index I as a direct variable for both iteration and memory access. Sixth, conclusion and next steps. We've successfully used a one-dimensional array to store and process a list of data efficiently, proving that arrays and loops are inseparable in C programming. Next up, we'll explore a very special type of array: strings. Our next lesson is 4.03. Strings. Strings in C as character arrays ending with the null character, \0. First, introduction. What is a string in C? In most modern programming languages, a string is a fundamental data type used to handle text. However, in C, there is no dedicated string data type. Instead, C handles text using the data structures we just learned: arrays. A string in C is simply a one-dimensional array of characters, char, that is terminated by a special character, the null character, \0. Second, the null terminator, \0, the strings rule. The most critical thing to understand about C strings is the null terminator, \0. The null character is a byte with a value of 0. It marks the end of the string. The C functions, like printf and future string functions we'll learn, use this \0 to know exactly where the text stops. Without it, the program would keep reading memory until it hit an accidental 0, which could cause errors. Example: the string hi is stored as 3 characters, h, I, \0. Third, declaration and initialization. Since a string is an array of characters, we declare it the same way. Method 1. Individual character assignment, manual. This is tedious and requires manually adding \0. Method 2. Using a character list. This is slightly easier, but you still need to remember the \0. Method 3. Using a string literal, the easiest way. When you use double quotes, the C compiler automatically converts the text into a character array and adds the \0 for you. Key takeaway. When initializing a string with a literal, double quotes, always remember that the array size must be 1 greater than the number of visible characters to hold that invisible \0. Fourth, accessing and printing strings. We access individual characters using the same zero-based index as any other array. To print the entire string, C provides a special format specifier, %s. When printf sees %s, it starts printing characters from the array's starting address until it encounters the null character, \0. Fifth, example code. The null terminator in action. This example clearly demonstrates the role of the null terminator. Conclusion from example. The printf function stopped printing the string right after the space because we replaced the character at index 2, I, with the null terminator, \0. Sixth, conclusion and next steps. A string in C is not a data type, but a concept, a null-terminated character array. The \0 is the rule that makes everything work. The next lesson is 4.04. Strings, Declaration and Basic String Functions Introduction to string.h. First, introduction. Beyond manual manipulation. In our last lesson, we learned the fundamental rule of C strings. They are character arrays ending with a null terminator, \0. We even learned how to truncate a string by manually inserting a \0. While this is true, it's not efficient. C provides a powerful standard library, string.h, which contains pre-built functions to handle common string tasks safely and quickly. Second, declaring strings, review and input buffers. There are two primary ways we declare strings, based on our needs. First, initialization, when we know the text content at compile time. Second, as a buffer when we need to store user input. We declare an array of a fixed size, creating an empty buffer to hold future input. Third, the scanf %s problem. The most basic way to get string input is using scanf with the %s format specifier. The major flaw, scanf with %s stops reading at the first white space, a space, tab, or new line. If you type New York, the output will be you live in new. This is unreliable for most real-world input. While better functions like fgets exist, in stdio.h, we first need to learn how to manipulate the strings we have. Fourth, the string library, string.h. To use C's built-in string functions, you must include the header file at the top of your code. #include string.h. This library gives us access to many functions. Let's look at the 4 most essential ones. Fifth, essential function 1, string length. Purpose, strlen, string length, counts the number of characters in a string up to, but not including, the null terminator. Syntax, size t length equals strlen, my string. Size t is just an assigned integer type. Sixth, essential function 2, string copy. Problem, you cannot assign strings using the assignment operator. Char dest sub 10. Dest equals hello error. You can't assign to an array address. Solution, string copy, copies the characters from a source string into a destination buffer. Syntax, string copy, destination, source. Seventh, essential function 3, string concatenate. Purpose, string concatenate, appends one string to the end of another. It finds the \0 in the destination and starts copying the source string from that point. Syntax: string concatenate, destination, source. Eighth, essential function for string compare. Problem: you cannot compare strings using the equal to operator. If string 1 is equal to string 2, error. This compares memory addresses, not content. Solution: string compare compares the content of two strings alphabetically. Syntax: integer result equals string compare, string 1, string 2. Return value: result is equal to 0 if the strings are identical. Result is less than 0 if string 1 comes before string 2 alphabetically. Result is greater than 0 if string 1 comes after string 2 alphabetically. For beginners, just remember, if string compare returns 0, they are equal. Ninth, conclusion and next steps. The string.h library is essential for C programming. It allows us to move beyond manual character manipulation. Today we learned string length for length, string copy for copying, replaces assignment operator, string concatenate for joining, replaces plus operator, string compare for comparing, replaces is equal to operator. In our next lesson, we will move from one-dimensional arrays, lists, to two-dimensional arrays, which allow us to store data in a grid. Our next lesson is 4.05. Two-dimensional arrays, introduction, the concept of matrices. First, introduction, from lists to grids. So far, we have learned one-dimensional, 1D, arrays. These are perfect for storing simple lists. A list of scores, a list of ages, or a list of characters, a string. But what if we need to store data that isn't a simple list? What if we need a grid, a table, or a matrix? Think about a tic-tac-toe board, a chessboard, or a spreadsheet with rows and columns. To store this kind of data, we need two-dimensional, 2D arrays. Second, what is a 2D array? A 2D array is simply an array of arrays. A 1D array is a row of elements. A 2D array is a collection of those rows, stacked on top of each other to form a grid. It has two dimensions, rows and columns. Third, declaration of 2D arrays. To declare a 2D array, you must provide two sizes in two sets of square brackets. Data type array name, number of rows, number of columns. Example, this code declares a 2D array named matrix. It has 3 rows. It has 4 columns. The total number of elements it can hold is 3 times 4 equals 12 integers. Fourth, accessing elements, double indexing. Since 1D arrays use one index, array sub I. A 2D array requires 2 indices to access an element. Array name sub-row index sub-column index. Just like 1D arrays, 2D arrays are zero-based for both rows and columns. Rows. The first row is index 0. The last row, in an array with 3 rows, is index 2. Columns. The first column is index 0. The last column in an array with 4 columns is index 3. Example. Using our integer matrix sub-3 sub-4, matrix sub-0 sub-0 equals the element at the top left corner, row 0, col 0. Matrix sub-1 sub-2 equals the element at the second row, third column. Matrix sub-2 sub-3 equals the element at the bottom right corner, row 2, col 3. Fifth, initialization of 2D arrays. You can initialize a 2D array when you declare it using nested curly braces. Each inner set of braces represents one row. Example, a 3 by 2 matrix, 3 rows, 2 columns. MyGrid sub-0 sub-0 is 10. MyGrid sub-1 sub-1 is 40. MyGrid sub-2 sub-0 is 50. Sixth, full code example. Let's see it in action. Expected output. Element at sub 1 sub 2 is 23. Element at sub 0 is now 99. 7th, conclusion and next steps. Today we learned that 2D arrays are arrays of arrays, perfect for storing grids or matrices. We access elements using two zero-based indices, row, column. This is the last lesson in our section on arrays and strings. In the next and final part of this section, 4.06. Exercises, no answers. Array 1. Input a one-dimensional array of integers. Write a program to output the elements that are Armstrong numbers. 2. Input a one-dimensional array of integers. Write a program to calculate the sum of the palindromic numbers. 3. Input a one-dimensional array of integers. Write a program to print out the superprime numbers in the array. 4. Input a one-dimensional array of integers. Write a program to find the smallest element in the array. 5. Given a one-dimensional array of integers, write a program to find the largest even number that is smaller than every odd value in the array. 6. Given a one-dimensional array of integers, write a program to print out adjacent elements that are both even. 7. Given a one-dimensional array of integers, write a program to find the last odd value in the array. 8. Given a one-dimensional array of integers, write a program to count the number of occurrences of each element in the array. 9. Given a one-dimensional array of integers, write a program to output the element with the most occurrences. 10. Given a one-dimensional array of integers, write a program to find the kth largest element in the array. 11. Input a one-dimensional array of integers. Write a program to sort the elements in this array in ascending order. Then print the elements to the screen. 12. Input a one-dimensional array of integers. Write a program to sort the elements in this array in descending order. Then print the elements to the screen. 13. Input a one-dimensional array of integers. Write a program that allows deleting an element at any position k. Then print the remaining elements in the array to the screen. 14. Input a one-dimensional array of integers. Write a program that allows adding an element with value m at any position k. Then print the elements in the array to the screen. 15. Given a sequence of positive integers a1, a2, and write a program to delete all the maximum values in the array. 16. Given a sequence of positive integers a1, a2, and write a program to remove elements that appear more than once. 17. Given a sequence of positive integers a1, a2, and write a program to insert the element 0 before each prime number in the array. 18. Write a program to find the greatest common divisor of all elements in a one-dimensional array of integers. 19. Write a program to find the least common multiple of all elements in a one-dimensional array of integers. 20. Given a one-dimensional array of integers, find the value in the array that is furthest from the value x. X is entered from the keyboard. 21. Given a one-dimensional array of integers, write a program to find all subarrays of the original array. A subarray is an array with a number of elements less than or equal to the original array, and the elements are consecutive. 22. Given a one-dimensional array of integers, write a program to find all increasing subarrays of the original array. String. Before doing the exercises in this section, you need to acquire some additional knowledge. First, you need to look at the ASCII table at this link. The table you see actually only has 3 columns of information because there are 128 characters, so they are arranged horizontally for compactness, probably. There are 3 columns of information: decimal, hex, and char. Now you only need to pay attention to decimal and char. Below are a few lines of code to help you understand the knowledge I want to convey to you. Integer. Char means converting the value of char type to the value of integer type. You can understand I to 97. I decimal equals 97. 97 in ASCII table is I. 97 minus 32 equals 65. Capital I decimal equals 65. 65 in ASCII table is I. Char. Capital I decimal means converting 65 to I. 1. Initialize a string. Write a program to print all characters in the string in uppercase. 2. Initialize a string. Write a program to print all characters in the string in lowercase. 3. Initialize a string. Count the number of words in the string. 4. Initialize a string. Count the frequency of each character in the string. 5. Initialize a string. Normalize the string according to the following requirements. No leading whitespace characters. No trailing whitespace characters. Each word is separated by only one whitespace character. Capitalize the first character of each word. 6. Initialize a string. Write a program to convert a number string to an integer word representation. 7. Initialize a string. Write a program to sort the characters in the string in descending order according to their ASCII values. 8. Extend a string to a palindrome. Given a string S consisting only of uppercase and lowercase Latin characters, capital A, capital Z, and a Z, find the minimum number of characters to add to the end of the string to make it a palindrome. 9. Initialize a string. Write a program to output the characters present in the string. Note: do not use the string.h library. 10. Initialize a string. Write a program to reverse the original string. Note: do not use the string.h library. 11. Initialize a string. Write a program to convert a string of digits into an integer. 12. Initialize an integer. Write a program to convert an integer into a string of digits. 13. Initialize a date string in the format day, month, year. Write a program to check how many days are in the month mm. 14. Initialize a date string in the format day, month, year, and initialize a variable containing the number of days. Write a program to calculate the resulting date after adding the number of days to the initial date. 15. Initialize two strings of digits x and y with a maximum length of 3. Write a program to add and subtract these two strings of digits.